Now, our theme for this year has been AI and how AI is kind of driving both the hardware and how hardware is driving AI. We've got a great lineup for you this morning and the rest of the day where we're going to really dig into this. We're going to dig into the infrastructure of how these connected devices are actually driving the world and how AI is actually being accelerated by the world of these connected devices. But before we actually kind of dig into our first keynote this morning that I'm very excited about, I'd like to actually just take a moment to thank our sponsors. So we couldn't do this without you and without our sponsors. Our lead sponsors today and for this entire event are Xilinx and Avnet. Our partners and teammates at Dragon Innovation sponsored our Hardware Boulevard. We've got a number of robot sponsors, including Autodesk, Microchip, Reliance CM. Give them a special little shout. They sponsored the cocktail party last night. Savvy, Rush Order, Whipsaw, Planet M, Breadware. All of these folks are also in our exhibit halls. So take a moment and go and visit them and share the love. They're sharing the love with you guys here, and so we so appreciate them being in the house. Also want to thank all of our other laser and machine sponsors. We just couldn't do this without all of this community that we've pulled together here. Now, yesterday, I did a call to the audience to see who was coming the furthest, and I know that we had folks from the Philippines and Hong Kong and China and India in the house. Anybody else want to shout out where they're from this morning?
Gilroy.
What's that?
Gilroy.
Gilroy, okay. Dude, you didn't even get traffic this morning, For those of you that don't know, Gilroy's just down the street, so. Arizona, all right. Well, we do have, the international group and gathering here at Hardwarecon. Also in our exhibits, you'll see some folks and friends from China and Hong Kong. And I'm really pleased this morning to be able to introduce our keynote, who is also not originally from the Bay Area. I don't think he lives in Gilroy. He certainly lives here now, but originally from Belgium. Ivo Bolsens is the CTO of Xilinx and has been since 2001. And if anybody knows the tech industry knows that that's actually a really very long tenure in these types of jobs. Xilinx has actually been working with a number of different companies, including Samsung and a number of different other partners and providers to really create the infrastructure and these differentiated devices that will help all of us create the next generation of devices, connectivity, and AI and ML that we're looking to pull together. Prior to joining Xilinx, Ivo was at IMEC in Belgium, a think tank, resource, and research group that's actually really looking to kind of move forward the future of technology there in the EU and really around the world. And so we're thrilled to have him and his team here with us today. And Ivo is going to be sharing with us today a keynote. I think that he's going to have some room for questions and answers, so think about what you want to ask. But he'll be talking with us today on delivering efficient and differentiated AI with adaptive and intelligent hardware. So I'm very much looking forward to this. Join me, please, in welcoming Ivo Bolsens.
Thank you for the introduction, and thank you for inviting me at this event. I had the opportunity to walk around a little bit before I entered in this room in the exhibition, and so there's really cool stuff going on, and I had the chance to talk with some of the people. If you have a chance, by the way, go and have a look at the Avnet and Xilinx booth, but another one, the Hackster booth, is really exciting, and especially also like there was a young lady there, who's kind of really gets you convinced about, the cool stuff that you can do with some of the latest technology. So I appreciated that discussion we had. And also, by the way, I'm the champion in Xilinx for women in technology, and I think you're a great example of that. So, having said that, I would like today to share you a little bit in some of our thinking in Xilinx and how it relates to this audience. And you know, yeah, I have to start with the megatrends. I think this is of course, the stuff you're all very aware of. What is driving our industry, and in terms of decision making, and in terms of identifying key technology challenges and opportunities. By the way, I don't know what's going on, but this screen is blinking on and off like crazy. If you can either leave it on or just switch it off, I mean, but it's kind of, all right, okay, good. Sorry for that. So there are clearly megatrends that influence us and that create opportunities for all of us that are somewhere at the background of some of the innovations. And these megatrends are, first of all, that we see clearly the emergence of the data centers and how people are more and more in many of their applications are relying on this widespread infrastructure. And interesting enough, these days we talk about data centers. When I was a young kid, I remember when I was doing computer science, I went to the computer center or the compute center. I forgot even how we called it. Now we call it a data center. There's a good reason for that. It's because it's all about the data. More and more, how you deal with data, how you organize data, how you transport data is defining the efficiency of what you're doing in your infrastructure. And then, a lot of, on the other side of that, you have, I would say, from the cloud, you have the edge, where you see major trends, where we see the IoT that is picking up, where we have this massive amount of connected devices and machines that take care of our safety, that protect us, that take care and monitor our health. And then ultimately we have devices on the edge that are moving us around, hopefully in the near future. With autonomous driving, that is clearly one of the most promising and exciting worlds. And then in between, you have the connectivity of all of that. You have 5G that is really starting to happen. It's starting to get deployed, definitely first in Asia, but we see it coming slowly to the US and hopefully at one time also in Europe. The 5G wireless that is going to allow us to have billions of devices connected and have bandwidths that are matching wired connectivity. So a lot of exciting stuff is going on at the background, on top of which a lot of innovation and opportunities are created for our industry. Now, if you look at these market trends and then you look at some of the technical challenges that come with this, is clearly, while all this is happening, one of the things, and me being in the semiconductor industry, of course, I'm kind of very well involved in some of these things. We notice that whereas we more and more need higher compute power or more efficient compute power, we see that Moore's law is starting to substantially slowing down, right? Some people say Moore's law is over. I wouldn't really say that, but it's definitely slowing down tremendously, and doesn't get us the return anymore that we typically have been used to. Which means, in all fairness, I keep on telling that for me as a CTO of a semiconductor company, it's kind of the golden age of innovation now. I mean, for many, many years, I had to fight the attitude of like, why would we take a risk in changing architectures or doing new things if we just go to the next technology node, we get its factor of 2 improvement. Now people are really, craving for new ideas, new architectures, new solutions. And so we clearly see that the traditional compute architectures are now moving into an all new area of massively parallel heterogeneous architectures that come with, of course, a whole bunch of challenges, but also with a whole bunch of opportunities. And I'll say a little bit more about that. On the other hand, as I said, whereas in the past, a lot of the innovations and so were driven by the need of computing, and I still see the industry, talking about teraflops and the likes. More and more, efficiency and differentiation comes with, how you deal with the data and how you process and store and transport the data. I mean, Cisco, predicted that in 2022, the internet will produce about 4.4 zettabyte of data. Well, I mean, that's like, 10 to the power with 21 zeros or something like that. So that's more data than the internet has, produced all the years before that year. And we are all looking at applications and opportunities to leverage that data that's been generated and to manipulate that data. So the data and how you deal with data becomes a very interesting challenge and an opportunity and differentiation. And when you talk about data, when you saw in the previous slide, when you looked at all these markets, if you look at this, if there is one common denominator in terms of foundational technologies that are going to move forward the needle in these worlds, it's the artificial intelligence. Interesting enough, about 30 years ago, well, it's probably longer than that now, I did my PhD on AI, and I was a weird guy at the time. People looked at me very kind of like a nerd that was a little bit out of touch with where the world was going. There was a lot of promise, but clearly the hardware was not living up to the expectations at the time, and as we all know, we went into what we as AI researchers called the AI winter, right? I mean, it was a lot of over-promising happening 30 years ago, but now we have the data, we have the compute capabilities, we have the infrastructure, and I really believe that AI is going to stay there and is going to be really foundational for a lot of the, the new opportunities. So let's, start by going a little bit into this, AI thing, right? I think, if you look at the pace in how a lot of AI technology is overtaking, how we look at problems and how we solve problems, it's tremendous. There's an exponential, growth in new technology that is emerging from the world of AI. And if you look, AI, one of the aspects, of course, of AI is neural networks. I mean, there's a lot more that comes with that. But if you just simply look at, neural networks, where I would say if you would identify the point where, we really saw like we crossed the threshold and people started to take AI seriously again, was around 2012, right? It was one of these famous competitions in image processing that suddenly started opening the eyes of a lot of people. And you clearly see that AI is moving into many applications from, image processing, recognition, detection, speech, towards, the more industrial side and anomaly detection and recommendation in processes and the likes engines. So you see a very broad applicability of AI. I think it will also replace, some of the older technologies in many of the applications. Now, if you look at what the pace is in how the innovation happens in AI, I just plotted out here a little bit like a slide of over time. If you think 2012 was kind of the tipping point where, with the famous publication on the AlexNet, as many of you might have heard of, you saw so many new neural network models being introduced. They're probably like relevant models every other month or so, something new that shift the bar of what you could do in a certain application domain has been coming to the forefront. And it will continue. We just are at the beginning of this, right? I mean, but just imagine if you're in a certain application domain, if you haven't looked at the literature for 3 months, you're outdated, I would say, if you're in the field of AI. And now that, of course, brings also some challenges in terms of if you want to build hardware, you know, that caters to that world. I mean, these days, if you, for example, if you want to build a chip, I would say, you know, it probably takes you 2 to 3 years from, you know, having a good idea of what you want to do towards finally having that chip into production. And this is probably, this is if nothing goes wrong, if everything works well. Now, can you imagine, you know, if you build a dedicated chip for a certain application, you nail down the specification, because then the train leaves the station and all the engineers start working on it. So, and then 3 years later, you have that chip in a product. Well, you know, 3 years is forever, right, in the AI world. And that brings challenges in, you know, what choices do you make, what architectures do you build in hardware that can cope, you know, with that fast pace of innovation, and that can allow and enable people to use the latest, you know, capabilities and technologies as they are coming towards us in the world of AI. Right? So there is definitely and I'm talking now as a silicon vendor, there is definitely challenges there in terms of, you know, by the time you have your silicon in product, it's almost outdated in terms of where people in the AI world are. So that's one of the challenges that comes with AI. The other challenge is also, you know, people always talk about computing and the need for compute and talk about figures of merit, and in many cases people, you know, refer to teraops or teraflops and see that as the simplistic way in how to measure, you know, the efficiency of a solution or something like that. Now, first of all, you know, when it's very different when you deal with computing in the edge or computing in the cloud. Although I would say they have all their root in the original CPU systems that, you know, one of the CPUs went basically forked off in the early days in 2 directions. One was in the direction of mobility and the smartphones, and that, you know, ended up into a lot of devices, you know, targeting to what today we would call the edge computing. And I would say, you know, architectures like ARM, and we see now RISC-V and so showing up in that world. And then the other fork was, you know, going more into the infrastructure side, the servers, the data centers, and now, you know, the cloud infrastructure, which is, you know, whether we like it or not, very x86 dominated. So now these 2 worlds also have very different figures of merit. You know, when you're thinking about cloud computing, things like real time are pretty important in many cases. It doesn't make sense, for example, to make a solution that is faster than it has to be, because if you do that, it means you're wasting resources in some way or another, right? So real time means just fast enough. You know, that's a completely different way in looking at how you build a system than when you're building a system for a big compute infrastructure in the cloud, where it's all about as fast as possible, right? Also, the architectures and the hardware that you're using in the edge, in many cases, you know, you require determinism, right? I would say if you have an embedded system that is servicing your brakes, you would like that every time you hit the brake, it's behaving exactly the same way as, you know, it did before. You don't want in any way or another kind of be dependent on some other threads that are running in your software, and you don't want to see a little circle going, you know, while you're hitting the brake or so. So determinism is really important in the embedded world, and latency is another one, right? I mean, in many cases you deal with systems that are somewhere in a control loop or in a feedback loop, and latency is sometimes more important than, you know, just the pure performance. And then finally, as you deal with things that are, you know, in a car, you know, you have systems that are sitting in the rear view mirror, that's sitting under the roof, with the sun blasting on your roof and temperatures that are very high, and you don't have a liquid cooling system or anything like that. So power is important. Power is also important as we go to electrical cars. You know, when people are, the only way I think electrical cars probably in the future will differentiate is how they look and how far you can get with them. And that's about it. There's no raving about the engines anymore. But one of the things is how far can you get with your car? And if you have your electronics eating, you know, battery power away, that will eat into your mileage, and that will be an important issue. So it's not all about just portability. It's about a lot of other things that are important when you deal with edge applications. On the infrastructure, on the other hand, it's about compute as fast as you can, you know, and another important aspect is scale out. You want to build hardware that you really can scale to millions of stamped out instances that can then be thrown at your problem at wish, right? So also there you see differences in the architecture. So what that means is we clearly see, you know, big changes happening both in the edge and in the cloud. And the cloud, for example, where you know, we have been for many years been used to a traditional, I would say, a CPU-centric type of architecture, you know, where you have CPU is the master, you know, the storage, the accelerators are somewhere sitting behind the CPU that controls everything, and then you have a network which is a pretty, you know, difficult to scale, tree-like structures with top-of-the-rack switches and then, you know, high-level switches and the like. Very hard to switch without, it was very hard to scale without degrading the performance of your overall infrastructure. We see now that we are going towards a much more network-centric architecture where you are disaggregating compute, storage, and acceleration, and where you basically can scale your architecture, you know, towards the problem at hand. You can allocate compute resources, acceleration resources, and storage resources that are, you know, specific for the application and the workload that you're working at. And so the solution is basically is your data center that's being configured, you know, towards an application at hand. And it's clear, for example, that the role of the network to transport the data back and forth and to deal, you know, with a specific application, that network will have to be programmable, has to be flexible. And, you know, if you are deploying 100,000, you know, compute nodes on a specific AI application, for example, you want to have, you know, a data transport infrastructure and protocol that is really tailored towards the needs of that machine learning application, for example. So clearly, you know, what we see on the cloud infrastructure side, a very disruptive story is happening there, where the architectures is changing of the overall infrastructure, and as a consequence, you know, the components that are part of that architecture also are showing to, are evolving in a pretty revolutionary way, I would say. So that's about the cloud. On the edge, you know, there are a lot of challenges. Of course, we all hear this event is also about AI and so, and we believe that AI is at the heart of a lot of opportunities in the future. But one of the key things is what we definitely have to keep in mind when we're talking about the edge. It's not just about AI. I mean, you're dealing with sensors which or actuators that are very different. You have different cameras, you have in the cars, you have LiDARs, you have sonar, and so ultimately your objective is to accelerate or optimize the whole application. And what people have to realize is that, you know, although AI and machine learning is becoming a growing important component of that, when you're building hardware, it has to be able, you know, to deal with the total solution, right? And you're as good as your weakest link in your application. And that's one of the things that I noticed with a lot of also the hardware startups. And so they're like, they're looking at this people optimization is like, oh, it's all about machine learning and I'm going to optimize for that. But they forget a lot of the other things that come around that. And another thing which is important is, of course, especially on the edge, it's not just about, it's important, the compute, the teraops per second and so on is important, but there are figures of merit that are at least as important, you know, when you deal with the edge and when you're building a hardware solution that you have to keep in mind. And things like the latency and of course the power consumption are very essential components that, you know, are as important, you know, as the compute capabilities that you're throwing at the problem. I used, you know, an example here, you know, so which is basically, suppose you're somewhere walking around and you want to know, you take a picture of a restaurant, you want to know when is this restaurant open. Now, yesterday evening when I was going through my slides, I realized this is a pretty stupid example because you probably would go to the door and check out, you know, what the opening hours are. But just for the sake of, you know, the exercise, bear with me, and I already had submitted my slides, so you know, I was not going to change that. But first of all, if you want to answer that question in the way I was explaining it, where you take a picture and you want an answer to one of the questions, that compute to answer that question, just as a background, is probably about 100 times more complex than when you do just a search on a Google search engine, for example. So the first observation is there's a lot of compute power that hides behind, you know, the way in how you would like this question be answered. The next thing is then when you look at what is the functions you need to solve that problem that you just stated, you know, take a picture and have a voice saying, you know, this restaurant, tell me when it's open. There is image processing, you know. You have to do scaling of the image, you have to do, you know, probably the energy has to be, or the brightness of has to be brought to a nominal level. That's a typical type of image processing applications. I would think if I was an engineer, I would look at, okay, what is OpenCV giving me here? How can I use these libraries and what can I do with that? Traditional DSP processing, you know. And then what you do is you have to kind of match the image with probably a database of restaurants and find out. So you might apply there some machine learning there. You might use, because it's image recognition, might use some convolutional neural networks or something like that. At the same time, you have to deal with the voice command that you got, and you have to figure out, okay, what is it? Is this a question or is this a command that I'm getting? If it's a question, you know, what kind of question is it? And you know, the kind of operations you do are very similar than you would find in some of the security applications, like regular expression mapping, which is bit level operations. You might have some natural language processing in there. And then finally, you know, you have to go to a database and do a search, which could be some structured data, so you can do, you know, it's a key value store problem. You use memcached or something like that for that. And so the point that I wanted to make here is, yeah, machine learning and AI is an essential part of answering, you know, that task. But there is a lot of other, you know, functionalities that come into play that have to do, you know, with data storage, that have to do with bit level matching, that have to do with image and speech recognition, different kind of neural networks, different kind of algorithms, different characteristics. So it's challenging, you know, to kind of map all of that onto an architecture that can handle it all. The other thing which I already mentioned is of course the latency, and I just want to give you one example here, what a hardware architecture can do, right? If you think these days and you think about you know, AI and automotive, a lot of people are thinking about GPUs, for example, right? And so you want your car to observe images and and give you commands in terms of, or take actions in terms of what's happening. Now, given the architecture of a traditional GPU or CPU architecture, I mean, these architectures are known for very high throughput, but have very low latency. So typically how these work, they work with batch mode. So what happens is, basically, at high bandwidth, the GPU takes a bunch of images, is then, after it has collected a bunch of images, will give you the outcome for, in this case, the 4 images. So it's more like, you know, I take in all these images. Oh, and by the way, the first image, too bad, but it was a pedestrian, right? So it processes this, you know, at a very high bandwidth, but the latency is the challenge. On the contrary, you know, if you would look at an FPGA, you can get the same bandwidth, but due to the architecture, you know, you have a different way, you can execute things in a more pipeline fashion. And so as a consequence, the latency, whereas the bandwidth is the same, the latency is much lower. So architecture matters. It's not just about teraops, it's about other aspects when you pick an architecture for these applications. And another thing, if you think about hardware, is happening in specifically about AI. Whereas, you know, not so long ago, you had all the compute benchmarks and everybody was talking about flops and teraflops and so on. Given the fact that, you know, efficiency of your hardware, cost of your hardware, power consumption of your hardware is becoming more important, it became clear that people really have to start thinking about optimizing on the arithmetic. And the good thing about something like AI is that, you know, accuracy of your arithmetic doesn't matter that much anymore. So whether you have a lot of flops, it doesn't really matter. You know, it turns out that there's a lot of things you can do if you reduce the precision, you know, of your arithmetic, and you can still get the same accuracy, you can get the same results, and you use far less hardware, and as a consequence, lower cost or lower power. Right? This diagram is from Bill Daly, who basically shows here that if you do a 32-bit floating point addition, you basically consume 30 times more power, you know, than when you do an 8-bit addition. Now, you will find out that in many of the machine learning applications, 8-bit is way enough, you know. I mean, people are now talking about binary neural networks where you literally, you know, do some of the functions, it's the same, I mean, XOR functions, basically. Right? So there's a lot changing there in terms of, you know, what is the good match of your hardware, what are the figures of merit, and especially if you have to work under constraints, right? So that means that, and that's the basically where we Xilinx are betting on a lot, is that we believe that there is a need, you know, to be able to tailor your hardware towards the domain of your application, and so that you can basically build hardware or program hardware, so you have an extra degree in your programming that allows you, for example, to customize how the data is being transferred in your system, that allows you to customize how the memory is being stored, and that allows you to customize how your arithmetic is being executed. And that's the strength that, for example, FPGAs bring to the table. And that's going to be essential, especially when you look at, you know, edge computing, but also when you look at, you know, the data center, when you see that whole plethora of applications that have very diverse type of requirements. As long as you can program your hardware to deal with that, that's, I think, an opportunity for the new field of, we call it domain-specific architectures, right? And now it's all easy to say that from a hardware perspective, but ultimately, you know, you need people that program these things, and you need to be, if you want to proliferate and unleash the full potential of such programmable, you know, very high degree of programmability in terms of data connect, in terms of memory architecture, in terms of precisions of arithmetic and so on. You know, that's a lot of degrees of freedom that is very difficult, you know, to deal with at a higher level for software people. So you want to make this potential of this hardware accessible to software people. And when we look at the software world, clearly there's a lot we can learn, you know, from the traditional, I would say, desktop software world, right? If you look at the world of programming, I would try to separate software methods in two ways. There is what I would call the software environments that are focusing on efficiency, and so people are talking about efficiency languages. To the extreme, if you're programming in an FPGA and you want to get the ultimate efficiency out of it, you go as far as dealing with very obscure programming languages like Verilog and VHDL, right? These days, the tools that are being provided by Xilinx and others allow you now to start writing, your functionality into C and C++ and OpenCL, so kind of get the level of abstraction higher. But still, I would classify this approach in the domain of efficiency. It's all about getting as much as possible out of your hardware. But then you have a whole world that's on top of that, which I would more call the world of productivity, where you want to have that really efficient implementation made available to a broad group of people who are not necessarily experts in the domain of the hardware, and can that just stand on the shoulders of these people that has implemented these very efficient libraries. And these people are used to what I would call productivity languages like Python and Scala, and are used to using frameworks like TensorFlow or FFmpeg or higher level of capabilities that are more tailored towards their specific domain of application. So that's a little bit, how you can classify the software world. And so what we looked at in Xilinx is we tried to learn some lessons from the Linux world. If you think about Linux, it's kind of like an inverse pyramid, right? You have probably a few hundred people that are really diehard experts, the kernel writers, the guys that, or the ladies that really, can commit code, to the kernel. And then as you go up, you have the device driver people, and then ultimately you have hundreds of thousands of people that are, standing on top of that foundation that is being created by, the few that really understand that. And so what we try to do in the world of FPGA, doing something similar, where, at the bottom level, you have a small group of people that can create these domain-specific architectures that are potentially even willing, to go and dig into VHDL and Verilog to build these. You wrap this into, C++ libraries, and ultimately you propagate and make these libraries available, to the people that, don't give a damn about whether, this is an FPGA or whether this is an x86 or whatever it is. They are interested in their domain of applications, right? And one of the efforts we started on that, for example, in Xilinx, is what we refer to PINK. And Python, PINK stands for Python on Zinc. And Zinc is our SoC product, which has the ARM processors in there. And actually, an interesting anecdote, the hardware boards that we have, some of the boards are actually pink, and that was one of my biggest struggles in the company, to have these boards available in pink color, because real engineers don't use pink or something like that, I guess. But you can actually see the boards out there. We have some of them. But ultimately what you do in the pink environment is you basically create libraries of downloadable domain-specific accelerators that are being created as overlays that you download in your FPGA fabric, and that you then package in your C++ library, and then you do a binding of that C++ with your Python. And all the software, you have a traditional Linux operating system, you have your Python kernel, you have, even on top of that, a Jupyter web server. All of that is running natively on the FPGA. So there is no CPU infrastructure involved. Everything is running natively, on the SoC system. And the only thing you use, of course, a terminal to display things. But that's kind of the way in how we see talking to the software community and making some of these challenges of domain-specific architectures and accelerators available to software people. So you basically package up these capabilities in a software-like environment, and you basically distribute these accelerators. And very simple, you go to GitHub, you do pip install of that accelerator, you have the Jupyter environment on top of that, and you start programming this system, leveraging the accelerator, and you basically don't really care whether this thing is running in FPGA Fabric or whether it's running on the ARM CPU. You don't need to know. It's running a lot faster. You have for example, a binary neural network that you accelerate on the FPGA, which can do the bit-level operations, which never works well in the CPU, of course. And you just pip install that library, and you get going in Python. So ultimately, what we are trying to do is we are making this kind of environment available in a scalable fashion. You have, I mentioned the pink, the pink PINQ board, but we have that software available in a whole plethora. There is the Ultra 96 board from Avnet that also been demoed here that has that environment available. That same environment is also available if you have an x86 plus a big accelerator, a big chunk FPGA is available. And then ultimately, the environment is also available on our new platform, and this is the only plug I put in there for the Xilinx products, which is the Versal product, which is a programmable platform. We refer to it as an adaptive compute acceleration platform, which has in the red, has the programmable logic FPGA, as some of you might know it, but also has, in the same vein, has 400 VLIW vector machines that are connected in a switch fabric available to deal with some of image processing, antenna processing type of applications, and then has multiple ARM application processors and real-time processors in there. So that environment will also cater to these Python programmers. And with that, I would like to thank you for your attention and open the floor for perhaps a few questions if there are.
Excellent presentation. I do the 3-day big data global conferences. I've done 20 of them, the largest ones. And good presentation. And I'm KRS Murthy. There is a lot of movement in the big data AI, ML area as well in multi-cloud management. Any comment on what are the things that are happening in multi-cloud management so that a customer, a company, enterprise can go through a portal and be able to store their data in any of the big or the small, whatever cloud companies, and then manage them, manage the cost, manage the workload, etc. on their own, rather than being stuck to one cloud company.
So is your question now related to, do you think that people will build on-premise solutions for their own application? Or
third-party companies can build one multi-cloud management platform so that especially small and medium enterprises would be able to go and not have all their data processed, stored, secured, whatever else features that are provided, and only one of them, like Microsoft Azure, or any one of them, AWS, etc. But you should be able to, across multi-clouds and their own private cloud, put it, process it, manage it, cost management, configuration management.
Yeah, well, I personally think that you will see a lot of scenarios from, I would say, on-premise towards public cloud and anything in between. You will see, I think specialized companies that will be catering you know, to specific niche use models. I don't think everything necessarily will end up into, you know, the Azure or the AWS type of clouds. And I think, I don't know whether it's here. I mean, for example, I know we're working with some companies like Nimbix is a good example, which is a smaller company that is trying to come up with solutions that are more customized to, you know, specific needs of different customers, but still offer an infrastructure service. And so I think you will see the whole plethora of things, but I definitely think, of course, public cloud is it's just at the beginning, if you ask me, in terms of, you know, how it's going to be leveraged, and especially if the IoT world is really picking up, you know, you will need a huge infrastructure behind that, and I think we are just at the beginning there. Yeah. Okay. All right. Thank you. Thank you. Thank you.